2.3 Second price auction. The second price auction or victory auction is an example of a game that has a weakly dominant strategy equilibrium. It is a sealed bid auction where bidders submit bids without knowing the bids of the other participants in the auction. The subject which is auctioned, the object which is auctioned is then assigned to the bidder who submits the highest bid, the winner, but the winner pays not her own bid, but rather the second highest bid, that is the highest bid among the bids that remain after removing the winner's own bid. Tie-breaking rules must be specified for selecting the winner when the highest bid is submitted by two or more bidders, in which case the winner ends up paying her own bid because the second highest bid is equal to the winner's bid. We first illustrate this auction with an example. Two oil companies bid for the right to drill a field. The possible bids are $10 million, $20 million, $50 million. In case of ties, the winner is player 2. This was decided earlier by tossing a coin. Let us take the point of view of player 1. Suppose that player 1 ordered a geological survey and, based on the report, concludes that the field would generate a profit of $30 million. Suppose also that player 1 is indifferent between any two outcomes where the oil field is given to player 2 and prefers to get the oil field herself if and only if it has to pay not more than $30 million for it. Furthermore, getting the oil field for $30 million is just as good as not getting it. Then we can take as utility function for player 1 the net gain to player 1 from the field defined as profits from oil extraction minus the price paid for access to the oil field. If player 1 wins and 0 otherwise. We have a grid of 5 by 5. Player 1 has the rows, player 2 has the columns. They have the same outcomes. 10 million, 20 million, 30 million, 40 million, 50 million. Same as for the rows as for the columns. 10 million and 10 million is 0. 10 million and 20 million, 0. 0, 0, 0. 20 million to 10 million. Player 1, player 2 is 20. 0, 0, 0, 0. 30 million, player 1, and 10 million, player 2. 20, 10, 0, 0, 0. 40 million, player 1, 10 million, player 2. 20, 10, 0, 0, 0. 50 million and 10 million, 20, 10, 0, negative 10, 0. Figure 2.10, a second price auction where, in case of ties, the winner is player 1. In figure 20.10, we have written inside each cell only the payoff of player 1. For example, why is player 1's payoff 20 when it bids $30 million and player 2 bids $10 million, since player 1's bid is higher than player 2's bid? Player 1 is the winner, and thus the drilling rights are assigned to player 1. Hence, player 1 obtains something worth $30 million and pays not its own bid of $30 million, but the bid of player 2, namely $10 million. It follows that player 1's net gain is 30 minus 10 million equals 20 million. It can be verified that for player 1, submitting a bid equal to the value it assigns to the object, namely a bid of $30 million, is the weakly dominant strategy. It always gives player 1 the largest of the payoffs that are possible, given the bid of the other player. This does not imply that it is the only weakly dominant strategy. Indeed, in this example, bidding 40 million is also a weakly dominant strategy for player 1. In fact, it is equivalent to bidding $30 million. Now, we can describe the second price auction in more general terms. Let n be greater than or equal to 2 be the number of bidders. We assume that all non-negative numbers are allowed as bids and that the tie-breaking rule favors the player with the lowest index among those who submit the highest bid. For example, if the highest bid is $250 and it is submitted by players 5, 8, and 10, then the winner is player 5. We shall denote the possible outcomes as pairs I, P, where I is the winner and P is the price that the winner has to pay. Finally, we denote by B sub I the bid of player I. We start by describing the case where there are only 2 bidders, and then generalize to the case of an arbitrary number of bidders. We denote the set of non-negative numbers by open bracket 0, infinity, close bracket, close parentheses. The case where n equals 2, in this case we have that capital I equals the 2 element set 1, 2. Capital S sub 1 equals capital S sub 2, which equals open bracket 0, infinity, close parentheses, and open interval. Capital O equals open curly bracket, open parentheses, I, P, close parentheses, colon. I is an element of capital I, which is 1, 2 in curly brackets, comma, P is an element of the open interval, close interval starting at 0, open interval at 50, close curly bracket, and F, colon, capital S yields capital O is given by F of the ordered pair B1, B2 in parentheses equals the set open parentheses 1, B2, close parentheses, if B sub 1 is greater than or equal to B sub 2. Next line, open parentheses 2, B sub 1, close parentheses, if B sub 1 is less than B sub 2. The case where n is greater than or equal to 2, in the general case, the second price auction is the following game frame. First bullet point, capital I equals open curly brackets 1 through n, close curly bracket. Second bullet point, capital S sub I equals open bracket 0, infinity, close parentheses. For every I equals 1 through n, we denote an element of capital S sub I by B sub I. Third bullet point, capital O equals open curly brackets, open parentheses 1, P, close parentheses, colon. I is an element of capital I, P is an element of open bracket 0, parentheses, close curly bracket. Fourth bullet point, F colon capital S yields capital O is defined as follows. Let H of B sub 1 through B sub n, close parentheses, be part of I, include set I, included or equal to the set I, be the set of bidders who submit the highest bid. Capital H, open parentheses, B sub 1 through B sub n equals, open curly bracket, I is the element of capital I, colon, B sub I is greater than or equal to B sub j. For all j is the element of capital I, close curly bracket, and let I hat of B sub 1 through B sub n be the smallest number in the set capital H of B sub 1 through B sub n. That is the winner of the auction. Finally, let B superscript max denote the maximum bid, and B superscript second of B sub 1 through B sub n the second highest bid. That is B super max of B sub 1 through B sub n equals capital M max, open curly bracket, B sub 1 through B sub n, close curly bracket, and B super second of B sub 1 through B sub n equals capital M max of the set B sub 1 through B sub n over the set B supermax of B sub 1 through B sub n. Then F of B sub 1 through B sub n is equal to, open parentheses, I hat of B sub 1 through B sub n, comma, B super second of B sub 1 through B sub n. How much should a player bid in a second price auction? Since what we have described is a game frame and not a game, we cannot answer the question unless we specify the player's preferences over the set of outcomes, capital O. Let us say that player I in a second price auction is selfish and greedy if she only cares about whether or not she wins, and conditional on winning, she prefers to pay less. Furthermore, she prefers winning to not winning, if and only if she has to pay less than the true value of the object for her, which we denote by V sub I, and is different between winning and is indifferent between not winning and winning if she has to pay V sub I. Thus, the ranking of a selfish and greedy player is as follows, together with everything that follows from transitivity. The ordered pair I comma P is better than I comma P prime for player I if and only if P is less than P prime. The ordered pair I comma P is better than J, the ordered pair J comma P prime for player I for all J not equal to I, and for all P prime if and only if P is less than V sub I. The ordered pair I comma V sub I is just as good as the ordered pair J comma P prime for player I for all J not equal to I and for all P prime. The ordered pair J comma P is just as good as the ordered pair K comma P prime for player I for all J not equal to I, K not equal to I, and for all P and P prime. An ordinal utility function that represents these preferences is superscript 7. Of course, there are many more. For example, also the following utility function represents those preferences. Capital U sub I of the ordered pair J comma P equals a set 2 superscript open parentheses V sub I minus P close parentheses if I equals J, and 1 if I not equal to J. Capital U sub I of the ordered pair J comma P equals the set of two elements V sub, the first is V sub I minus P if I equals to J, and the second is 0 if I not equal to J. Using this utility function, we get to the following payoff function for player I. Pi sub I of B sub 1 through B sub n equals a set of two elements. The first is B sub I minus B supersecond of B sub 1 through B sub n if I equals I hat of B sub 1 through B sub n. And the second element is 0 if I not equal to I hat of B sub 1 through B sub n. We can now state the following theorem. The proof is given in section 2.8. Theorem 2.3.1, Vickery, 1961, in a second price auction. If player I is selfish and greedy, then it is a weakly dominant strategy for player I to bid her true value. That is to choose B sub I equals V sub I. Note that for a player who is not selfish and greedy, theorem 2.3.1 is not true. For example, if a player has the same preferences as above for the case where she wins, but conditional on not winning, she prefers the other player to pay as much as possible. She is spiteful. Or as little as possible. She is generous. Then bidding her true value is no longer a dominant strategy. Test your understanding of these concepts introduced in this section by going through exercises in section 2.9.3 at the end of this chapter.